Hello everyone, my name is Cody. I'll be talking to y'all about nuclear fission. Pretty simple look at a very complex topic. So let's get started. So starting off, nuclear fission hasn't really been around for that long. It was discovered in 1938 by two scientists, one Lise Meitner and an Otto Frisch. They discovered it in December of 1938, and they actually published their article in January the very next month. Without getting too deep into a history lesson, that time was kind of tough for the world. There was a lot going on in terms of war, so this really influenced the way that fission was looked at and the way it was viewed, kind of what processes that it was originally developed for, and we'll get into that more in a little bit. So our outline of what we're going to talk about is what is nuclear fission? How does it occur? How does radioactive half-life affect nuclear fission? What nuclear fission has been used for in the past, and then what are potential future applications of nuclear fission could entail. So, what in the world is nuclear fission? It's a pretty complicated process, but I'm going to try to break it down as simple as I can. And to use my example, I'm going to use uranium 235. It's a pretty common atom used in nuclear reactors around the world, and you can find the most research on it outside in the real world. So, starting out, nuclear fission starts with an unstable atom, which in this case will be uranium 235. It's really relatively unstable compared to other atoms. And the first thing that they're going to do is bombard it with either one or a bunch of different neutrons. That neutron is going to impact that uranium 235 atom, essentially adding another neutron to the atom itself. This makes it very unstable. It pretty much splits nearly instantaneously, and when it does that, it becomes two stable atoms, or relatively stable atoms at least. In most cases, it'll split into xenon 140 and strontium 94, but it does split into a lot of other examples, such as like cesium, some different strontiums. It just depends how it breaks apart, and that influences the other atoms. So for this example, we'll use xenon 140 and strontium 94. So if you count it up, 140 and 94, you'll notice that it doesn't make 236 neutrons. There's still three left over. Those three left over continue to bounce off um, other atoms, other uranium 235's atoms in there, and that creates a chain reaction. So instead of just having one fission product, you now have multiple fission products, and it just keeps on breaking down more and more and more. So what happens with one, creates three, creates nine, creates 27. It just keeps breaking down exponentially. So, like, an easier way to picture this is think of it as like telling a secret. So, you have a secret and you tell three people. So now three people know. Well, those three people go out and tell three people each. So now you, those three people, and then nine more people know. You just keep doing this over and over again, and pretty soon everybody in the whole town is going to know your secret. You're thinking, I only told three people. So it's kind of like that. It just exponentially increases. So a good way to picture how much energy is released during these fission reactions is to kind of look at the half-lives and then look at how much exactly energy is released. So thinking in terms of half-lives, even though uranium-235 is a relatively unstable atom, it has a half-life of 703.8 million years. That's a long time. Now, when it splits, it could create xenon-140 and strontium-94. Xenon-140 has a half-life of only 13.6 seconds. Strontium-94 isn't much longer at 75 seconds. That's quite a bit of energy being released very quickly compared to a lot of energy being released over a long period of time. Now, some of the energy released during just one of these fission products will be approximately 210 MeV, which is mega electrical volts. And if you think about it, a large lightning strike could be anywhere from 20 to 100 MeV. Now, that is just one fission product's energy released. In the chain reaction, there could be hundreds upon thousands of them. So that's a lot of energy being released at one time. Now, today, nuclear fission is being used for really only two different things. One of them, which is potentially a good thing, is nuclear energy, where instead of using fossil energy and creating carbon emissions, we're using nuclear energy and it's creating clean energy in large amounts. Now, the other thing, which is what nuclear fission is kind of more commonly known for, is for large bombs, nuclear bombs. Since, we talked earlier about that time when it came out during the World War II era, that's when it was more looked at, was for that research more than for energy sustainability. It was more used as an offensive weapon. And we've seen in Japan those weapons used twice. One of those being a fission bomb, one of those being a fusion bomb. Now, nuclear fission in the future. The verdict still isn't in exactly about whether it's going to be a good thing or a bad thing. Personally, as an environmental scientist, I don't think it's a good thing. I'll tell you why. So, we've had a number of nuclear reactors, but we've also already had 12 major events. Some of the more popular ones being Chernobyl and Fukushima. We're still feeling the effects from Chernobyl, even though that was over 30 years ago, and it's expected to take thousands of years before the nuclear radiation is completely gone. So, the energy from that could be potentially very good, but it could also potentially be extremely harmful to all life on Earth. So, really, it's a pro con list, with, in my opinion, the cons being way more heavy than pros. So, kind of a summary of everything we've discussed. What really is fission? So we've talked about how fission happens, especially with unstable atoms, neutrons bombarding them, and the chain reaction it creates. So we talked about the half-lives and the amounts of energy that it creates. Just one fission product is easily double that of a lightning strike, and then you have thousands of fission products in one chain reaction. So we talked about how we use it today in nuclear reactors and then in bombs, which are still very prolific in this day and age. And we'll kind of talk about how, the verdict isn't up for nuclear fission in the future and what its potential uses are. So thank you for listening to me. Hope you all have a good day.